Hello everyone, good morning, good afternoon, good evening. Thank you so much for joining us today. My name is Caroline Maître and I will be your webinar host coming to you from Bordeaux, France. Today's webinar topic, we will be looking at wire harness design, an underappreciated secret ingredient of your aerospace success. I am delighted to welcome other speakers and experts today, Mr. Bartosz Czarnecki and Mr. Steve Caravella. So Bartosz is a technical product manager for electrical harnesses manufacturing solutions, and Steve is a solutions architect and market development for aerospace and defense. I will let them both introduce themselves, and thank you so much, gentlemen, for being with us today. So Bartosz, I will now pass you the ball and make you presenter so you can kick off this webinar.
Solid and robust harness design forms the foundation of a reliable, high-quality, and cost-effective product manufacturing to support on-time delivery. As a platform design moves from virtual to real product, the use of a configuration-controlled electrical digital twin brings critical advantages to the design of wire harness, essential in the modern aerospace and defense products. This webinar will discuss how improving your harness design tools and processes enable your business to meet today's challenges and bring success to your programs. Hello, my name is Bartosz. I'm Technical Product Manager responsible for electrical harness manufacturing suite. I collected my professional experience in the aerospace industry, working for the last 17 years for one of the world's largest aircraft supplier. I have been through every stage of electrical harness manufacturing and engineering, from the design through preparation and optimization of the process to the complete production process, including electrical testing. I had the privilege to leading various engineering groups, including manufacturing, license, and tooling engineering. Joining me today is Steve Caravella. I'll let him introduce himself.
Hi, everyone. This is Steve, and I work as a solutions architect in market development for Siemens Digital Industries software, with focus on aerospace and defense industries. I have 28 years experience in aerospace, working at aircraft OEMs, with expertise in the areas of engineering design, certification, and project management. During that time, I did engineering design and provided sales support, manufacturing support, and field support. I've led engineering and certification teams in development of new products, active production, aircraft outfitting, and modification and retrofit projects. We will start off the conversation today looking at industry trends that have developed during the past decade, and Bartosz will start us out.
There are at least 4 major trends that are important to the programs and businesses. First, the industry is undergoing a tremendous amount of change. Many aerospace programs are either over budget, late, or both. The pressure to reduce program cost and schedule while meeting requirements is one of the big challenges. Second, at the same time, aerospace programs are becoming increasingly complex and highly integrated. As companies seek to improve their product performance, reduce weight, or provide more functionality, they seek integrated solutions and are relying on more software. This increased complexity creates challenges in designing, manufacturing, and certifying new products and bringing them to market quickly.
We're also seeing more electrification of products. Some of this is driven by the desire for greener solutions. Some is driven by increased automation or autonomous vehicles that increase demand for software. And some companies are replacing mechanical systems, such as hydraulics, with electrical systems to improve reliability and maintainability. And finally, there's an increasing global regulatory oversight. Major efforts over the last decade to delegate authority to OEMs has been progressing, but not at the pace desired by the industry. Recent high-profile events have not only raised public attention to product safety, but have also caused regulatory agencies to increase direct involvement in certification activities. Companies need to get ahead of this, and one way to do this is to improve the design process and complete design validation earlier in the development process. This can be onerous and time-consuming, but there is hope. One step companies are taking is going digital with product design and carrying that through the value stream. Today, we are going to look at areas where this effort is being applied to the design of wire harnesses.
The aerospace industry faces many challenges, but there are three main ones which we will tell you about. The first one is quality of the product, a factor that directly affects people's lives. On one hand, we have the high demands from the industry. On the other hand, there is a big emphasis on the quality of the engineering work. How do you determine whether your product is of good quality? First of all, you need to establish a reference quality standard. The required product quality is not an option, it's an absolute requirement. Often people focus on achieving the best possible quality, but it is not the quality standard. Sometimes everything you can give is still not at required level, and on the other hand, it may happen that you have reached a level much higher than required. In both cases, this is not what you want to achieve. So what is the challenge? You must achieve the required level of quality, which is defined by the standard. For example, certain value of connection resistance. Your company can have expectations of 0 defects, but some variations can be acceptable. Having the clear understanding of quality standard is essential. For example, the dimensional accuracy and the tolerance.
Delivery of product is the top priority for our companies. It's not only how we keep our customers happy and meet their needs, but also it is how we make money. There are lots of challenges that happen daily to put our product delivery at risk, ranging from material shortages to just tight schedules to begin with. This becomes even more difficult when we are faced with unplanned errors and rework. We may think about on-time delivery as one of the core competitive factors of our business, but it is more than that. Ultimately, we need to have control on our delivery schedule, and the better we are able to forecast and execute on that commitment, the more successful we will be. With receipt of revenue being dependent upon product delivery, it is tempting to focus on making delivery as early as possible. However, this focus doesn't cause us to recognize and address disruptions to our system. A better thing to focus on is a reduction of lead time, or you could think of it as cycle time, and boosting our responsiveness. We will talk more about how better design process and tools can help with this challenge, but first Bartosz will talk about a third challenge.
Have you been thinking what is the purpose of any company in the aerospace industry? We'll say the purpose of the business is to make money. It's stated in 1970 by the economist Dr. Milton Friedman that the purpose is to generate profits for its shareholders. Any form of operation generates revenue, but on the top of that, there are costs, which reduce your profit. The main components of cost are labor, materials, services, etc. To reduce the cost, sometimes you need to take the definition of your process and see which elements you can not only reduce, but eliminate. Sometimes some activities which you consider value added, in fact, are unnecessary costs. Some cost drivers are out of our control, so we need to focus on those costs we can control, such as labor cost, rework, warranty cost. Can you reduce the cost thus increasing your margin? Of course you can, and you will find it out later how to do this using capital. Does these challenges sound familiar to you? Have you ever had an opportunity to face those issues in your field? For me, it was an everyday job. Working in aerospace industry, it's all part and parcel of it. Let's take a closer look at traditional approaches and how we can utilize a new approach to better meet these challenges.
So let's start by taking a look at a traditional process to harness design and the steps companies take to address errors and issues in that process. So a traditional harness design process typically involves creating a 2D wiring diagram of the design. This diagram is then sent over to mechanical engineering to design a 3D routing of the installation. Along with the wiring diagram showing connections, the mechanical engineer needs to know a number of wire bundle parameters as well as some design constraints. Usually this information is calculated manually using spreadsheets and then communicated by email. Mechanical engineers enter this information into their models and they complete the routing. This sets the geometry for the overall harness. The wire length and branch location information then gets sent to the harness engineer to create the harness layout and the design. The harness design is often done in the form of stick line drawings, which define and illustrate the different lengths and branches of the harness. The fabrication team will use the stick line drawing to develop a form board to lay down the wires and may also need to reference the wiring diagram to determine how to pin the connectors. With so many manual steps and disconnected information transfer in between, it is expected that mistakes will be made and changes will be required, such as those listed. These types of mistakes will not be uncovered by bench testing of the harness, and therefore most companies must deal with this at the time of installation. The first build of the product reveals a lot. The effort requires MRB or liaison engineers at the final assembly floor to help investigate and resolve issues, and may include engineering inspection points. Issues are resolved and documented through a formal discrepancy resolution process, which can be cumbersome and time-consuming. The bottom line is that while companies may be accustomed to handling the shortcomings of the traditional disconnected process and have procedures and staff in place to address all these issues, there's a major weakness in this process, and it all centers around the manual and disconnected design process, which can only go so far in preventing design errors. A lot of energy, manual design checks, and cross-functional design reviews go into minimizing mistakes, but the effectiveness is ultimately limited and highly dependent based on people's individual experience and their focus. You can think as complexity grows and the pace of change grows with it, it will be extremely difficult to sustain the business using this quote-unquote tried and true approach. So let's look at a simplified example how this approach affects the design and manufacturing cycle.
This example will demonstrate to you what is the impact of engineering effort at the different stages of the development life cycle. Let's assume we've got 100 designs. Let's take a look at the graph, which represents the typical development life cycle: design, manufacturing, and installation. Let's put on the graph 100 designs, manufacturing of 100 harnesses, and 100 mistakes. Even if 1,000 details are correct, always will appear one, which will make your product wrong. Let's assume that each harness has one mistake. That ends up with a total of 100 mistakes found in the harness installation. 99.9 accurate with 1,000 of details in each harness, it still means one detail is wrong. The yellow curve represents the engineering effort through the steps of the process, ending at the installation. You will see there are multiple weeks of design activity. Then the harness will go to fabrication, where the engineering support may be needed to address manufacturing issues, but ultimately, most design mistakes will not be discovered until installation and test, requiring high level of engineering support in a short period of time. At this point, this effort is completely unplanned and carries the high level of urgency equivalent to an AOG situation. Installation is the worst place to find and correct mistakes. What if we could improve to be more like the blue line? With better process and better tools, maybe we will be able to reduce the engineering effort, but more importantly, if we can eliminate mistakes, we can significantly reduce disruption downstream, reduce rework, less schedule risk, less non-value added costs because it is waste. Why don't we take a deeper look at the industry challenges? Let's look at the three areas and focus on the quality. Let's address what we need to improve. You remember the two main quality areas, the quality standards required for production and engineering. But how this relates to the design of the harness? The specifics of the production makes it impossible to detect design errors at the production level through electrical testing. At the end of the production, you will be able to detect manufacturing errors, such as mispinned connectors, poorly seated pins, poor quality connection caused by bad crimping. On the other hand, you cannot detect design errors such as poor component selection or missing wiring. You cannot compensate the poor design by doing the harness testing. You will only find out about them at the very final stage, for example during the installation, which is already very challenging. At this stage, is your attention mainly directed at correcting the original design? In my experience, this is the point at which you put the most of emphasis on fixing the defects to keep production moving, for example involving MRB engineering, on all the other costs associated with rework, which I will talk about later. Ask yourself, if design would be always correct, do you need MRB?
Next, let's talk about delivery. Delivery is a key business driver, and we face the risk of delays due to disruptions in many areas. Some of these things are out of our control, and the best way to prepare is to be ready to address them as they arise. But what about the ones we can control? Specifically, if we can reduce design changes by eliminating errors found downstream, we can reduce the risk to delivery. The correction and resolution of errors found during manufacturing is time-consuming and burdensome and puts the schedule at risk. Problems found at the very end of the process dramatically reduce the ability to recover the delays and multiply the cost impact. Some of these disruptions include repeated removals and installations, which drive repeated testing and troubleshooting, delays in getting updated documentation and approvals to move the work forward. And finally, the more issues that are found, the less confidence there is in the design and the build, which can lead to increased inspections. Ultimately, it is extremely important that we make our delivery commitments, where we face financial penalties that not only affect our bottom line, but also affect our reputation in the market.
Let's talk about the cost. Cost is not only the price of materials, production time, or engineering time. It is also the repair time, overhead time, additional inspections, unplanned costs associated with scrap, rework, and the all too familiar huge cost of EOG. Well, yes, it makes me realize that what we see as a direct cost is just the tip of the iceberg. The majority of true costs are not visible at first glance, while its effect on profitability is substantial. Does it recall any analogy? Well, yes. The Titanic paid dearly for not seeing what was under the iceberg. The most of you are familiar with those problems and factors involved. Let's talk next about how we can address them. Some of the leading companies are turning to digitalization for help. Now we will take a look at the approach.
So with the question being, how can we do better? We think at Siemens here that use of a digital twin is part of the answer. Ideally, this is done for the entire product, and I'll explain this in terms relative to designing an aircraft. Developing a digital twin of the aircraft for multiple design disciplines and connecting those together so the information can be accessed directly or transferred digitally creates a digital thread supporting information flow up and down the design and manufacturing chain. This approach creates a virtual copy of the design, which can be validated electronically against design rules, and eliminates the need to manually transfer and to transcribe information between the design disciplines. So what does this enable? It enables us to integrate disciplines, teams, and domains for seamless data sharing and reduce delay during handover. We can have early and frequent analysis to reduce the risk by validating systems prior to and during implementation. We can optimize designs, production, and product utilization using simulations. And then we also get requirements traceability. Since we're specifically talking about wire harnesses today, Bartosz can frame it in that context.
Wire harness design is a part of electrical system design, and here at Siemens we've got the capital software to handle this. Digital twin is a virtual representation of a real harness, its manufacturing process, and what more, its maintenance. This allows all kinds of simulations and analysis to be performed without the use of complex mathematical models, product prototyping, and mental triage. Digital twin gives you the opportunity to switch from reaction mode to prevention and detection mode at the early stage. Following the principle, prevention is better than cure. How does it work? How to prepare it? Creating a digital twin is much easier than you expect. Combine the aircraft harness topology and wire connections and create a comprehensive model which enables a digital process. The result is a virtual harness model that contains not only its geometry, but all the wiring data. This combination creates a solid basis for further processing according to individually tailored requirements and unique to your customer or business model. With this step behind us, we open up a pool of all possibilities that capital offers. Let's look at this in another more simplified way. If we consider how the digital twin and digital thread bring value, We can view this in terms of value pyramid. The model of the design forms the foundation for the value pyramid. The model, as the digital twin, can contain more information than normally captured in a traditional 2D drawing and bill of material of the design. The second layer is validation that includes automated design checks. No more human iterations at this level. System can make the verification based on the standard or customized rules. Let me show you some of them. Here are some examples of applications and areas where they can be used. One of them is connectivity. It gives you the possibility to check, among other things, if all your wires have terminations at both ends, if they are not left unconnected, if there are no empty harnesses. Connectivity is where it starts, and next we look at the validation of wiring and parts. Another element of DRC is range. Range defines the limits within which a parameter must be contained. This can be, for example, the minimum maximum cable length, the cross-sectional range of cable, or electrical connection parameters such as temperature range or environmental resistance. The system checks whether the length and diameters comply with the requirements. It also automatically verifies that the parts you are using are in accordance with the specifications in the library and they are not out of date. Library rule check assures that the materials you're using are allowed to use and approved for production. It checks that each has all necessary documentation and approvals. The next thing we can check is consistency and compatibility of the components. System can check whether all connectors are electrically connected, whether the contacts match the connectors, or whether sealing plugs used are appropriate. On the other hand, inclusion will check if you have used the right substitute when needed, if it is available, or you have obtained the right material compatibility. These are just examples, but each company has its own rules specific to a particular project or type of the harness. You are free to create rules, assuming all sorts of conditions must be met. We continue building the value pyramid. Beyond the validation, we've got the traceable flow. We have built the foundation, we have checked it by design rule checks. And what now? How has it changed the process?
Now that we've talked about a digital approach utilizing a digital twin and digital thread, let's see how the design process changes compared to the traditional approach we looked at earlier. First, the design process is digitally connected, and the connection crosses multiple disciplines. In the example of creating a harness design, new tools such as Capital enable the digital bridging and syncing of design details from the wiring diagram to the mechanical engineer. Likewise, the 3D routing information can be digitally passed to the harness design. Manual calculation, data interpretation, and transcription are eliminated, along with the opportunity for mistakes. Because the model contains more information than traditional design formats, the harness design information starts off highly enriched, enabling not just lengths and branch positions to be included, but also things like pin-to-pin connectivity, cavity materials and sizing, and even bend radius requirements for the bundle. The result is digital synchronization of the design elements, eliminating mistakes and rework, both during the design process and, more importantly, at the final manufacturing points. One of the major positive effects this will have that is not often considered is this improved accuracy can significantly boost the reputation of the engineering teams that are responsible for those designs. Even though engineering teams get thousands upon thousands of details correct, it is the errors that create disruption and impact that is seen by the entire organization. Here, the bottom line is this: the connected process helps ensure consistency and accuracy of the harness design. Bartosz will explain how this flow works using Capital.
This well supports typical flow, which starts with the harness engineering, taking the advantage of rules-based engineering, like automated part selection, styling, calculation, and the checks we talked previously. This is the simplest way to create the model, which, as you remember, is the foundation of the value pyramid, and is treated as a basis for the rest of activities. Modular XC allows you to create and enrich a virtual product. This is the moment when you synchronize the 3D model of the harness with the connection list. This is what is called the creation of the digital twin, as you have just seen. All the above activities are done automatically and verified by design rule checks. By continuing to use the modular XC, you will decompose the harness into subassemblies by functional or production modules or derivatives. Using the add-on tool FormBoard XC, you can create your foam board ready for manufacturing. The tool will guide you to configure in the most optimal way, taking into consideration ergonomic zones, which are the most comfortable for the operators. What more, you can automatically merge two similar harnesses, creating one comprehensive foam board. The structured bill of processes presents a virtual twin of the production process. At this stage, with the use of the program TVM, you can create your own set of manufacturing tasks required to do the assembly, and the system will guide you through all steps to prepare the best manufacturing scenario. Once you have your harness prepared and have done all the calculation based on the production sequence you created, you can perform costing of your product. You can make comparisons in order to assess the cost impact of the modification or configuration you are carrying out on your harness. The final stage of the process is the preparation execution of production. Here you will perform line balancing with the line balancing tool. You will save a lot of time and iterations. The system, taking into account workstations, material, and flow, will optimize your production line, leaving it in the most efficient configuration. At the very end, having the design created and corrected, the manufacturing process is established and optimized, you can create your own personalized work instructions using Capital workbooks. They will reflect all manufacturing steps, all needed components and materials for every single manufacturing stage, including tools and jigs required to perform the process according to the quality standard. This concludes the development of the production process. You have created a model ready to reuse. You have generated the bill of process on the basis of which you have established time and material cost calculations. Your production line is optimized, and you have all the necessary instructions and the layout on which you will manufacture the harness. And this is how you move from what, which is the harness product engineering, the model that forms the basis of the value pyramid, to how, to a digitized production process, optimized and ready to use in the production workshop. This is the model of a seamless, fully digital engineering and manufacturing process. We have been focusing on the first three layers of the value pyramid because those represent such a significant opportunity for companies without going as far as rethinking the whole design approach. The one additional thing we want to mention is what is really at the top of the pyramid. This is the use of automation with design rules and processes to enable automatic generation of designs which are correct by construction. Generative design can offload the design team from much of the laborious tasks associated with design evolution, assessment, and evaluation by developing design solutions that meet the criteria specified upfront. However, it is important to highlight that this builds from the bottom up, and your company will realize value as you build each layer of the pyramid. So let's wrap up discussing the benefits of this approach, in particular using capital for electrical system development. And what does it give you? There are three main benefits of using capital, which are key to your success. Automate and manage, build a solid foundation, take advantage of all the opportunities that come from seamless data flow. Reduce program risk and achieve planned levels of quality, timeliness, and profitability. Forget about multiple iterations. Get your product right first time. No more costly tryouts, reworks, nor delays. Capital is a quite mature software. Many customers using our software have achieved measurable benefits that are available also for you. You can significantly reduce the number of design changes resulting from production, prepare the correct foam board faster, or reduce the schedule. This all leads to tangible profits, which contributes to an increase of your revenues. In addition, you can get the product right first time by avoiding harness scrapping. And here are some real-world examples. Our customers have seen benefits such as 90% reduction of design changes, 85% saving in the foam board design, and 3 months reduction in schedule. A robust harness design has been shown to achieve first time right and thus avoid costly scraps. Our partners from space and aeronautic industry trust us and have achieved this.
I hope that this webinar provided you with some new insights into how digitalization and advanced tools can help to get better at managing change and ways to use that to your advantage. So I'll leave you with one final question. How can your organization get better at harness design? And with that, we'll conclude today's presentation. Thank you.
Thank you.
With that, I would like to thank again our presenters and experts today. So Mr. Steve Caravella and Mr. Bartosz Swarneski. Thank you so much, gentlemen. If you have an immediate project, so don't hesitate and you can give us a call to get you started. And thank you all for joining and for your interest in our Siemens Global webinars. I will now close the session. Goodbye.